We continue our study of logarithms. In this video, we'll solve logarithmic equations and exponential equations. Get your notes ready, grab a chair, and let's go. Precalculus Online starts now. Let's take a look at 5.6 logarithmic and exponential equations. So we're going to go through a variety of equations here and talk about how to solve them. So the first example, we want to recall that y equals log base b of x is actually equivalent to b to the y is equal to x. And so changing a log equation into an exponential equation is sometimes very helpful to solve. Example 1, solve for x. Log base 7 of 4x plus 5 equals 2. So if I just revert this back into an exponential equation, I get 7 squared is equal to 4x plus 5. And now the x is free from the log, and we can solve for x. 7 squared is 49 is equal to 4x plus 5. Move the 5 over, you get 44 is equal to 4x. Divide by 4, and you get x is equal to 11. So that's one example. Second statement, if log base b of m is equal to log base b of n, then the arguments are equal. So the m is equal to the n. So if you have two logs that are equal, as long as they're in the same base, then their arguments are equal, and you can just set them equal. Example number 2, solve. Log base 3 of x minus 4 is equal to log base 3 of 5. So in this case, the x minus 4 is equal to the 5, and x is equal to 9. Example 3. Example 3, we get into a little bit of a harder one here. Solve for x. Natural log of x plus natural log of x minus 3 is equal to the natural log of x plus 5. So we don't quite have the previous situation where we have log of something is equal to log of something. But is there something I could do on the left to create a single log? And the answer is yeah, I can combine them. Since they're added, then I can multiply the arguments. So we get natural log of x times x minus 3 is equal to the natural log of x plus 5. And now that I have two logs that are equal to each other, that must mean that their arguments are equal. So I can drop the logs, and I get x times x minus 3 is equal to x plus 5. I'll go ahead and distribute here, and we get x squared minus 3x is equal to x plus 5. We have a quadratic, so to solve a quadratic, I move everything to the left. We get x squared minus 4x minus 5 is equal to 0. This factors, and it factors as x and x, 1 and 5, and the 5 has to be negative, the 1 has to be positive. Then to solve this, set each of these equal to 0 and solve. So we get x is equal to negative 1 and x is equal to 5. But that's not quite the answer. And here's why. When you do log problems, you do need to check the domain. And remember that the log in any base of x must satisfy that the x be greater than 0. Now the x is sort of a generic placeholder here. What this means is whatever it is you're taking the log of has to be positive. Can't be 0, and it can't be negative. So I have to make sure that each of the three logs that I'm using in the original statement of the equation would still be taking the log of a positive when I plug in the two answers of x equals negative 1 and x equals 5. So, well, right off the bat, we put in negative 1 and we get the natural log of negative 1. That's a non-starter. So negative 1 is not a solution. that is out. Then you can check the other three. So when x is equal to 5, or the other solution with the 3 logs. So when x is equal to 5, we have natural log of 5, that works. Natural log of 5 minus 3 is the natural log of 2, that works. And the natural log of 5 plus 5, which is the natural log of 10, and that one would work. So everything works with x equals 5, and the only answer is x equals 5. Another way to think about this is just to produce the domains of each of these functions. So the natural log of x has a domain that is x is greater than 0. The natural log of x minus 3 has a domain that is x is greater than 3. And the natural log of x plus 5 has a domain of x is greater than negative 5. Then you use the most restrictive. Of these to produce the domain that works for this entire equation. The most restrictive is x is greater than 3. And then check your solutions. Is negative 1 greater than 3? No, so that's out. Is 5 greater than 3? Yes. So that one works, and so 5 can be allowed to be a solution. Next we have solve exponential equations. So to solve an exponential equation, we just want to get the x to the baseline and then solve everything else around it, just like we would normally. There are a couple of ways to do this. Let's solve this one. 8 to the x power minus 5 equals 15. So I'd move the 5 over. We get 8 to the x is equal to 20. And then what does this mean in terms of logs? Well, it means that log in base 8 of the answer, 20, is equal to the exponent. But that's exactly solving for the x. X is equal to log base 8 of 20. And that's one potentially good answer. That's a correct answer. It's fine. It works out great. Here's another way of doing this problem, though. You can take 8 to the x and move the 5 over and get 20. Then you can take the log on both sides, and you can actually do it in any base that you want. So one common base that we use very often is natural log. So I'm going to take the natural log on both sides. We get the natural log of 8 to the x is equal to the natural log of 20. Then, using my log rules, the x as an exponent can come down in front. And we get x times the natural log of 8 is equal to the natural log of 20. Finally, the natural log of 8 is just a number. And so I can divide on both sides, and I get x is equal to the natural log of 20 over the natural log of 8. And you may think, well, I got two different answers. Which one is correct? Well, it turns out they're both correct. These are equivalent. And there's even a little rule that goes with this called the base changing rule. And the base changing rule says the following. Log in base b of x is equal to log in base c of x divided by log in base c of b. So b can be the original base, and it becomes the argument of a pair of the logs in another base. So c here is a different base. In this example, the c is actually equal to the number e. So it would be natural log of 20 over natural log of 8. So these two are equal. Example 5, solve. 2 raised to the x plus 5 is equal to 7 raised to the 3 minus x. So a couple of problems here. You may want to take a log on one side, on both sides, but which side would you choose as the base, the 2 or the 7? Well, the 2 and the 7, they don't work very well together. 7 is not a power of 2, so that's problematic. So usually the way we handle this is we rely on the natural log. So let's take the natural log on both sides. And we get the natural log of 2 raised to the x plus 5 power is equal to the natural log of 7 raised to the 3 minus x power. Then we have these powers. We have x plus 5, and that's going to come to the front. And we have 3 minus x, and that's going to come to the front. We have to be careful because what we're bringing to the front is not a single number or symbol. It's an expression. So that expression needs to go in parentheses to make sure the distribution is still correct. So we have parentheses x plus 5 times the natural log of 2. And that's equal to, parentheses, 3 minus x times the natural log of 7. And now, believe it or not, this is just a linear equation. And so we distribute, get x's on one side, get all the numbers on the other, and solve for x. Looks a little complicated because of the logs, but it's straightforward. Traditionally, we put the log stuff on the right side. So this is x times natural log of 2 plus 5 natural log of 2 is equal to 3 natural log of 7 minus x times the natural log of 7. Any term with an x stays or goes to the left side. Any term with no x, with just numbers, are going to go to the right side. So we're going to get x natural log of 2, the negative x negative x times the natural log of 7, that's going to move to the left. It's going to become positive. And we get plus x natural log of 7. That's going to be equal to 3 times the natural log of 7 minus 5 times the natural log of 2. Notice that we have an x on both terms, so we can factor that out. And that leaves us with natural log of 2 plus the natural log of 7 is equal to 3 natural log of 7 minus 5 natural log of 2. And the final step is to divide by this coefficient right here. And so we get 3 natural log of 7 minus 5 times the natural log of 2 over the natural log of 2 plus the natural log of 7. And that's the answer. Now, this is the exact answer. Okay. Some people confuse what the exact answer is with the decimal approximation. You could plug this into your calculator and get a decimal, but the decimal is not going to be exact because these natural logs of 2s and 7s, they don't terminate in the decimal. So that would go on forever. When you're getting a decimal, you are approximating the answer. The exact answer contains the natural log symbol that represents the natural logs of 7 and the natural logs of 2 in this case. Let's look at example number 6. Solve 9 to the x minus 7 times 3 to the x minus 18 equals 0. So this one looks a little bit odd. We have x as an exponent of two different numbers, but notice that the two different numbers have a relationship. They're 9 and 3. If it's possible, what we want to do is sort of write them the same way so that we can work with them. And indeed we can. 9 turns out to be 3 squared raised to the x minus 7 times 3 to the x minus 18 equals 0. But 3 squared to the x is the same as 3 to the 2x, and everything else is the same. And then I can split this up sort of going backwards. 3 raised to the power of x, and then that entire quantity squared. And that's what I want to do. And I wanted to show you all the steps here just so that you can see where it goes. A lot of times what we do is we just go straight from even the first equation down to this one, or at least the second one down to this one, where these two exponents, they can sort of switch around. But now this is what we have, and I'm going to use substitution, and I'm going to let u be a new variable that represents 3 to the x. And I'm going to substitute into this last equation that I have here. So this is going to be u squared minus 7u minus 18 equals 0. Now we have a quadratic. Factor the quadratic. We get u and u. What two numbers multiply to give you 18 and subtract to give you 7? That would be 9 and 2. The 9 needs to be negative, the 2 needs to be positive. Set each of these factors equal to 0 and solve. So we get u is equal to negative 2. And then u minus 9 equals 0 gives me u equals 9. Now we must back substitute. Because we're not solving for u, we're solving for x. And then what was u? Well, first of all, u was 3 to the x. That's equal to negative 2. This equation has no solution. Because if you remember, the exponential function never is negative, at least not without some transformations. All right. Well, if it says that 3 to the x is equal to negative 2, that means it would have to intersect somewhere down here at negative 2, but it never goes below 0. So there's no solution to that equation. Now, it doesn't mean there's no solution for the whole thing. It just means that one didn't give us anything. Let's look at the next one. 3 to the x is equal to 9. That's a good one. What numbers, 3 to what power gives me 9? That's a 2. It's because it's 3 squared. So x is equal to 2. All right. And for this last one, it's pretty much already done for you. What you need to do is you want to solve this equation right here. The trick to solving an equation is to let one side be y1 in the calculator, let the other side be y2 in the calculator. And the solution, the x, is the x-coordinate where these two graphs intersect. So I've set up y1 is equal to x times e to the x, and I've set up y2 to be equal to 6. y2 equals 6 is the horizontal line that you see here. And x times e to the x, very strange function. We don't know what that looks like when we graph it. That's why we need the graphing calculator to help us on this one. Turns out to be this curve right here. And then wherever they intersect, you can get that x value, and that's the answer. The intersection of these, once you graph it on this window, you can find the intersection by using second calc, and then number 5 is intersect. When you do the intersection, it'll ask you for one graph, hit enter, a second graph, and the cursors automatically jump to the next graph if you only have 2 in there, hit enter, and then it'll ask you for a guess. If you have multiple intersections, then you want to be close to the intersection point that you want. Hit enter again, and it'll produce this intersection right here. And so the solution for x that we're looking for is x is equal to 1.432, rounded to 3 decimal places.